Roots of a complex number. General polar form. For the next application of de Moivre's theorem, it is necessary to be able to write a complex number in general polar form. This involves writing the angle, the argument, of the complex number in a more general form. From trigonometry, we know that we can add any whole number of circles to an angle, and the cosine and sine remain unchanged. Likewise, we can subtract any whole number of full circles from an angle, and the cosine and sine will also remain the same. Formally, cos theta is equal to cos theta plus n times 360 degrees. And sine theta is equal to sine times theta plus n times 360 degrees for n elements of the integer set. So from minus infinity to minus 1, 0, 1, 2, 3, and on to positive infinity. So just not for rational numbers or complex numbers. Thus, if z is equal to r times cos theta plus I sine theta, which is equal to r cos theta, then we can also write z equal to r cos theta plus n times 360 degrees plus I sine theta plus n times 360 degrees, which is equal to r cos theta plus n times 360 degrees for n elements of the integer set. This is called the general polar form of the complex number. So, to write a complex number in general polar form, step 1, calculate r and theta as usual and write it in polar form. And part 2, add plus n 360 degrees or plus 2n pi if using radians to the angle. So, write z equals 1 plus I in general polar form. So again, we draw out our Argand diagram. This is our imaginary axis, this is our real axis. We plot the complex number 1 plus I, which is about here, so it's in the first quadrant. We join that complex number to the origin and label that line as r, so that's our modulus. And we drop a perpendicular from the complex number straight down to the real axis. Here we have our angle theta in the center. It's our reference angle, but it's also our angle theta because we're in the first quadrant. We don't have to change anything. So 1 is opposite the angle theta and 1 is adjacent to angle theta. So r is equal to the square root of 2 using Pythagoras' theorem, and the angle theta is equal to 45 degrees using TOA. So tan is equal to opposite over adjacent, which is 1 over 1, which gives us 45 degrees if we're in degree mode. Then, in polar form, we get z equal to r cos theta. So z is equal to root 2 cos 45 degrees plus I sine 45 degrees, which is equal to root 2 cos 45 degrees. So in general polar form, z is equal to root 2 cos 45 degrees plus n 360 degrees plus I sine 45 degrees plus n 360 degrees, which is equal to root 2 cos 45 degrees plus n 360 degrees for n elements of the integer set. The kth roots of a complex number. Consider the equation z to the power k is equal to alpha, where alpha is an element of the complex number set and k is an element of the natural number set, and k is greater or equal to 2. By putting both sides of the equation to the power of 1 over k, we can write the equation as z equals alpha to the power of 1 over k. So raising z to the power of k to the power of 1 over k, raising the power to a higher power, we multiply the powers, and k, which is really k over 1, multiplied by 1 over k, just gives us 1. So z to the power of 1 is just z. But if we raise the left-hand side of the equation to the power of 1 over k, we must raise the right-hand side of the equation to 1 over the power of the k. So we get alpha to the power of 1 over k. So solving for z, we get z equals alpha to the power of 1 over k. This equation has k individual roots called the kth roots of alpha. To find all the roots, we must write in general polar form and use de Moivre's theorem. Ordinary polar form will only give us one root, The following example shows us how we find all the roots. Find all the roots of the equation z cubed equals minus 2 plus 2i for z elements of the complex number set, and write your answers in the form of or cos theta plus I sine theta. So we start by writing minus 2 plus 2i in general polar form. So draw our Argand diagram. Here's our real axis, here's our imaginary axis. And minus 2 plus 2i lies around here. We join that complex number to the origin, creating the modulus, which we label as or. We drop a perpendicular from the complex number down to the real axis. This is the opposite of our reference angle, and that is a distance of 2. And here we have the adjacent to our reference angle, and that again is a distance of 2. So our angle that we're looking for, theta, is actually here. So or is equal to the square root of 2 squared plus 2 squared, which is equal to root 8, which is 2 root 2. So that was using Pythagoras' theorem. Then to find our reference angle, tan of or is equal to the opposite over the adjacent, which is 2 over 2, which is 1. So or is equal to 45 degrees. So our reference angle is 45 degrees. So to find theta, since we're in the second quadrant, we take our reference angle away from 180 degrees. So that's the rule for the second quadrant, if that's where your complex number lies. So theta equals 180 minus 45, which is 135 degrees. So our angle theta is 135 degrees. So in general polar form, minus 2 plus 2i is equal to or cos theta, which is 2 root 2 cos 135 degrees plus n times 360 degrees plus I sine 135 degrees plus n times 360 degrees, which is equal to 2 root 2 cos 135 degrees plus n times 360 degrees for n elements of the integer set. Now we rewrite the equation to get z on its own, and then we will use de Moivre's theorem. So we were given z cubed equals minus 2 plus 2i, and we worked out in the previous slide that minus 2 plus 2i is actually 2 root 2 cos 135 degrees plus n times 360 degrees. So to the power of 3 actually becomes a third when we carried over the equal sign. So we have all of this to the power of a third. And we take the or, which is 2 root 2, and we just raise that to the power of a third. So 2 root 2 to the power of a third is just root 2. But for the angle, we're going to use de Moivre's theorem. So we're going to multiply the angle by the power. So cos 135 degrees plus n 360 degrees, we're going to multiply by a third. So the third comes down in front. So it's going to be a third times 135 degrees, which is 45 degrees, or a third of 135 degrees is 45 degrees. And also a third multiplied by 360 degrees, or a third of 360 degrees is 120 degrees. So we're left with z equals root 2 cos 45 degrees plus n times 120 degrees. So to find the 3 individual roots, we put n equal to 0, 1 and 2. So remember, z is to the power of 3, which means it has 3 individual roots. If it was to the power of 4, it would have 4 individual roots. If it was to the power of 5, it would have 5 individual roots. So we have z equals root 2 cos 45 degrees plus n times 120 degrees. So when n is equal to 0, so we swap that n there for 0. 0 times 120 just cancels. So we get z equals root 2 cos 45 degrees, which is equal to root 2 cos 45 degrees plus I sine 45 degrees. So basically you just forget about this part. When n is equal to 1, so we're going to have 1 here, 1 times 120. We get z equals root 2 cos 165 degrees, because 45 degrees plus 120 degrees is 165 degrees. So we get root 2 cos 165 degrees plus I sine 165 degrees. And when n is equal to 2, so if we have a 2 here, we get z equals root 2 cos 285 degrees. So 45 plus 2 times 120 is 285 degrees. which gives us root 2 cos 285 degrees plus I sine 285 degrees. So, in example 2, putting n equal to 3, 4 or 5 would just repeat the same roots. So for the first root, z can be seen here with an angle of 45 degrees. For the second root, z can be found here with an angle of 135 degrees. For the third root, it would lie here with an angle of 285 degrees. And for the fourth root, you would basically just end up back at the first root. And for the fifth root, you would just end up back at the second root. And for the sixth root, you just end up back at the third root, and so on. So it would just repeat itself. So since z was to the power of 3, the circle is actually broken up into 3 equal pieces. The roots in example 2 are shown on the argon diagram opposite, as we just went through. As the roots have the same modulus, they all lie on a circle with the centre the origin. The radius of this circle is the cube root of the modulus of z. The first root has an angle 1/3 that of z, then the other roots divide the circle into 3 equal parts. A similar analysis may be made for the roots of any complex number. The kth roots of unity are 1. The roots of the equation z to the power k equals 1 are called the kth roots of unity, or 1. Although they can be found in the same way as in example 2, they satisfy some interesting properties. Example 3 outlines and derives some of these properties. Example 3, find all the roots of the equation z to the power k equals 1 and show that these roots can be written as 1, w, w squared, w cubed, w to the power k minus 1, that w to the power k is equal to 1, and that 1 plus w squared plus w cubed plus w to the power k minus 1 is equal to 0. Example, find all the roots of the equation z to the power k equals 1 and show that these roots can be written as 1, w squared, w cubed, w to the power k minus 1. Okay, so 1 is really equal to 1 plus 0i, because 1 has no I stuck onto it, so it's the real part. So 1 is equal to 1 plus 0i, which on our argon diagram would be the coordinate 1, 0. So here's our real axis, here's our imaginary axis. Here is 1 on our real axis, so this is the point 1, 0, so it's the complex number 1. Notice that it has an angle theta of 0 degrees because it's on the positive part of the real axis, and it has an or a modulus of 1. So thus or is equal to 1 and theta is equal to 0 degrees. Hence z is equal to or kiss theta. So we're going to let 1 equal 1 kiss 0 degrees plus n 360 degrees. And since 0 plus 360 degrees is 360 degrees, we get 1 equals kiss n 360 degrees for n elements of the integer set. So the equation can be written z to the power k equals kiss n 360 degrees. The k comes over the equal sign and becomes to the power of 1 over k. So we get z equals kiss n 360 degrees to the power of 1 over k. We're going to use de Moivre's theorem and multiply the angle by 1 over k. So we have z equals kiss 1 over k times n times 360 degrees. So we get z equals kiss n times 360 degrees all over k for n elements of the integer set. So the roots are, if n is equal to 0, so we swap this n here for 0, we get 0 times 360 degrees, which is 0. So we get 0 over k, which is just 0. So z is equal to kiss 0 degrees, which is cos 0 degrees plus I sine 0 degrees, which is equal to 1. Because cos of 0 is 1 and sine 0 is 0, so I times 0 just cancels, so we're just left with 1. Next, if n is equal to 1, so we're going to have 1 here. 1 times 360 degrees is just 360 degrees. So get z equals kiss 1 times 360 degrees, which is 360 degrees over k, which is equal to w to the power of 1. So we are just stating that KISS 360 degrees over K is equal to W. When n is equal to 2, we have 2 multiplied by 360 degrees over K. So 2 times 360 degrees over K gives us KISS 360 degrees over K to the power of 2. So this is de Moivre's theorem in reverse. So, which is basically KISS 360 degrees over K, which is W, but we're squaring it, so we've W squared. So when n is equal to 2, we get W squared. When n is equal to 3, we swap this n for 3, so 3 times 360 degrees. So we get KISS 3 times 360 degrees over K, which is going to give us KISS 360 degrees over K to the power of 3. So again, de Moivre's theorem in reverse. And since we stated up here that KISS 360 degrees over K is equal to W, then KISS 360 degrees over K to the power of 3 must be W to the power of 3. And lastly, we want to show that the roots can be written as W to the power of K minus 1. So if n is equal to K minus 1, we're going to multiply K minus 1 by 360 degrees. So get Z equals KISS K minus 1 times 360 degrees over K, which is going to give us KISS 360 degrees over K to the power of K minus 1. So again, using de Moivre's theorem in reverse. And again, since we stated KISS 360 degrees over K to be equal to W, then KISS 360 degrees over K to the power of K minus 1 gives us W to the power of K minus 1. So we've shown that the roots can be written as 1 W, W squared, W cubed, dot dot dot, W to the power of K minus 1. Part 2, show that W to the power of K is equal to 1. So using the same idea from part 1, we swap the n for K, so we get KISS K times 360 degrees over K. The K's will cancel, so we've got KISS 360 degrees, which is equal to cos 360 plus I sine 360, which is equal to 1. So cos of 360 degrees is 1, and sine of 360 degrees is 0, and 0 times I will cancel out the I. So we have shown that this is equal to 1. Or, as W is a root of the equation Z to the power of K, which is equal to 1, we can substitute W for Z, and so we get W to the power of K is equal to 1. So we want to show that 1 plus W squared plus W cubed plus dot 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 W to the power of K minus 1 is equal to 0. So we're going to let A equal to 1 plus W squared plus W cubed plus dot 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 W to the power of K minus 1. Next we're going to multiply every term on both sides by W. So A times W is WA, 1 times W is W, W times W is W squared times W is W cubed times W is W to the power of 4, and so on. And if our final term had been W to the power of K minus 1, then getting rid of the minus 1, our final term is now W to the power of K. And we know that W to the power of K is actually equal to 1. We worked it out in part 2. So now what we've written here, which is highlighted in green, is actually what we have written up here, just in a different order. The 1 is now at the back, whereas the 1 had been at the front, but otherwise it is the exact same. So we can now substitute this for A, because we had A equal to this. So we have W, A, is equal to A. We're going to bring that A over the equal sign, it becomes minus A, and we let that be equal to 0. We're going to factorize the A out, so we have W minus 1 times A is equal to 0. And then we're going to divide both sides by W minus 1 to get the A in its own. And 0 divided by anything is 0, so A is equal to 0. On an Argand diagram, the kth roots of unity lie on the unit circle. The first root has an angle 360 degrees over K, and from here the roots divide the circle into K equal parts. The diagram opposite shows the positions of the roots of the equation. So Z to the power of 5 is equal to 1. So we can see that our circle has been broken down into 5 parts. So we have 1, 2, 3, 4, 5 complex numbers. So the positions of the roots are 1, W, W squared, W cubed, and W to the power of 4. So whatever power we have for our Z, we subtract 1 to get the final W. So this was z to the power of 5, so we go up to the power of 4. If this was z to the power of 6, we'd go up to the power of 5. If this was z to the power of 8, we'd go up to the power of 7, and so on. So we have 1, w, w squared, w cubed, w to the power of 4. And we would basically just keep repeating that if we were to go on to higher powers. One of the other properties of the roots of unity is visible on this diagram. For every non-real root, its conjugate is also a root. Recall that the conjugate of a complex number is the reflection of that number in the real axis. On the diagram, w and w to the power of 4 are reflections of each other in the real axis, and so are conjugates. So we can see that these are reflecting each other in the real axis. And the same applies to w squared and w cubed. They are reflecting each other in the real axis. It can also be shown that if w to the power of p, where p is greater or equal to 1 but less than or equal to 4, is a root of the equation, then so is 1 over w to the power of p. This is because 1 over w to the power of p is equal to w to the power of k divided by w to the power of p, because we know that 1 is equal to w to the power of k. And when we're dividing powers with the same base, we subtract the powers, so get w to the power of k minus p, which is one of the other roots. So for example, 1 over w squared is equal to w to the power of 5 over w squared, which is equal to w to the power of 3, because 5 minus 2 is 3. A special case of the kth roots of unity is the roots of the equation z cubed equals 1, which are called the cube roots of unity. In an exercise, you'll be asked to show that these roots are 1, w, which is equal to minus a half plus root 3 over 2i, and w squared equal to minus a half minus root 3 over 2i. Then, to show that 1 plus w squared is equal to 0, it is only necessary to add the real terms and add the imaginary terms. For the cube roots of unity, we can rearrange 1 plus w squared equal to 0 to get 1 plus w equals minus w squared. Basically bring the w squared over the equal sign, it becomes minus w squared. So we get 1 plus w squared, so now we're bringing the minus w squared back over the equal sign to get positive w squared, and we're bringing the w over the equal sign to get minus w. And finally, we can bring the 1 over the equal sign to become minus 1, and the minus w over the equal sign to become positive w. So there are many ways to rearrange these, and we may use any of these at any stage in different questions. So this is specifically for the cube roots of unity. So that means z to the power of 3. So we go up as far as w squared. So 1 plus w squared is equal to 0. And there are many ways we can arrange this. And we will use different arrangements of it in different questions. So you want to watch out to see if these pop up, because if they do, you can substitute. So for example, if 1 plus w came up in one of your examples or one of your questions, you could substitute it for minus w squared. If 1 plus w squared came up, you could substitute that for minus w, and so on. If w is a non-real root of the equation z cubed equals 1, show that 1 plus w times 1 plus 2w times w squared minus 1 is equal to 3. So let's start off with the first two brackets. 1 plus w times 1 plus 2w. We're going to break open this egg, so we're going to have 1 times 1 plus w times 1 plus w. 1 times 1 is 1, 1 times 2w is 2w, w times 1 is w, w times 2w is 2w squared. So we're going to rearrange them so that the 1 comes first, then we have w, then 2w, and then 2w squared. So we're going to factorize out the 2, so we have 2 times w plus w squared. So notice that we have w plus w squared, so we can use one of our equations that we set up in the previous slide. So one of those equations was w plus w squared equals minus 1. So we swap this for minus 1. So we get 1 plus w plus 2 times minus 1. 2 times minus 1 is minus 2. Minus 2 plus 1 is minus 1. So you get w minus 1. So this is equal to w minus 1. So we swap this for w minus 1 with brackets. And now we're going to multiply in the w squared minus 1. W times w squared is w cubed. W times minus 1 is minus w. Minus 1 times w squared is minus w squared. Minus 1 times minus 1 is plus 1. Now, we know that w cubed just ends up back at 1. Because z to the power 3, we have the roots to be 1, w, and w squared. So w cubed ends up bringing us back around to 1. So we just swap w cubed for 1. And then we have minus w squared. So we're going to factorize out the minus. And we have w plus w squared. And we bring down the plus 1. And notice that again we have w plus w squared, which we know is equal to minus 1. So we have 1 plus 1, which is 2. Minus minus 1, which gives us 3. So we have shown that this is equal to 3. So just another reminder about the argument of a complex number. If the complex number is in the first quadrant, then the angle is just equal to the reference angle. Theta is equal to the reference angle. If the complex number is in the second quadrant, we subtract the reference angle from 180 degrees to get angle theta. If the complex number is in the third quadrant, we subtract the reference angle from 180 degrees and then add on a minus to get theta. And if the complex number is in the fourth quadrant, then to get the angle, we just add on a minus to the reference angle.